So we go on to our composite panel, and we're looking at the same input parameters. We've got panel depths ranging from 50 millimeters to 200 millimeters, and we've now got spans ranging from 2.4 millimeters to 6 meters. There's a reason I've made the arrays the same size, because it makes it much easier to produce the graphs at the end. So it's the same procedure as we've had before, except because you've now got a matrix of numbers, you have to do these things in stages. So we start with bending, and again, you're looking at the familiar bending equation turned on its head. You see what the force is, and then you take out the span dependent part of that and put that separately. So if you think about WL squared upon 8, you're flipping it on its head, so you need the L squared underneath. So we create a variable called LM for each of those and multiply it by effectively the force. And we come out with this matrix, and I think it's a 7 by 7 matrix, giving the unit load for each thickness and each span, hence a load span table. Similarly, we do shear capacity checks. Here's your spans that we're considering, and I'm using my convention again. If I've declared a variable before, but I'm declaring it again, I just put it in grey. And the shear is going to be proportional to the length, so put 1 over the L to give you one array, and then we multiply that by what's effectively the shear force there to give you the loading which would cause the panel to fail in shear. A quick comparison, you don't really need to do this, but it's a nice to have. Take one from the other. So once you've got these matrices, you can do matrix mathematics on it, and all sorts of fun can be had. In this case, you can see that for any span bigger than 2.4 meters, then bending is going to be more dominant than the shear. But for under 2.4 meters, the shear will be dominating. Now we're looking at deflection checks, and to look at deflection checks, we have to look at the transform section. So you've seen that before, but this time we're getting bigger. We've got elastic moment capacities as before, therefore we redefine what the elastic bending failure limits are. So here is the load for each of these thicknesses at each of these spans. So for a 6 meter span for a 200 mil thick panel, it can take 1.39 kilopascals before it fails in bending. Okay, then we look at the deflection, and again we're limiting the deflection to span over 150. I'm looking at a simply supported span, and hey presto, out comes the load. And keen-eyed will spot it. How on earth did you jump to that? What on earth is this DD? Well, all the complicated calculations have been hidden away in an area, so let's expose that. And yes, there they are. So Mathcad allows you to put in areas which you can hide, which allows you to do intermediate stages of your calculations as you need, as you go along. So most of these figures are fairly meaningless to the final value and fairly meaningless to anyone checking it, except if you really want to check it line by line. And because it's a matrix, you can't do everything all at once. And you rumble through all of these stages, you add them all together and come out with the deflection limits. So you want to ramp that up from a serviceability deflection limit to an ultimate deflection limit. And then you can create your DP thicknesses versus your spans for your ultimate limit state. Again, a little comparison, you don't have to do it. It just shows you that for 50 mil thick panels, your deflection is governing, and beyond that, your bending is governing. We can look at fixing loads. So if you set your fixings at 1 meter centers, you can get your kilonewtons per meter in effect. More realistically, your fixings are going to be at 200 mil centers. And that's what the fixing loads are, given the maximum bending load you're putting on. But if you've got a fixing capacity fixed at 2.7, for example, you can then calculate what your spacing is before your capacity of your fixing is exceeded. You can then repeat the procedure for your 2-span continuous, and then we're looking at wind pressures. So these are the fixing loads under each of the wind pressures, low, medium, high, and so forth. You can go into what's the deflection under unit load. This is a bit of a sidetrack, not entirely necessary. And then we can look at the bending capacity for each panel for each thickness, and then superimpose on that the high, very high, medium, and so on, the wind speeds across that. So this is for bending failure. We can do the same plot for shear failure, and then another plot for deflection failure. So these are the loads that would cause the panel to exceed deflection limits. And we can plot on the loadings for fixings at 1 meter spacing, fixings at 200 mil spacing, and so on. So that brings me to the end of the composite panel.